Welcome to the first video in Chapter 4, Section 2. The topic of this section is logarithms and logarithmic functions. And the goal is to be able to evaluate logarithms and to graph logarithmic functions. So here the objectives are define logarithmic functions, sketch logarithmic functions, rewrite logarithmic equations as exponential equations, and rewrite exponential equations as logarithmic equations. In this video, we're going to see where logarithms come from. So say you got an equation like this, 300 is equal to 2 to the x, and your math teacher tells you to solve for x, and you go, wait, x is an exponent, how in the heck do I get x out of the exponent and to isolate it? Because remember, when you're solving an equation, the goal is always x equals some number or numbers. But how do I undo an exponent, getting an exponent? Like a root wouldn't do it. A root is like how if you, like x squared is equal to some number like 4, you undo squaring by square rooting. But here, like the variable is an exponent, so rooting isn't going to help. It's not the tool to use. Well, I could use my knowledge about, powers of 2, like 2 to some power is 256. And then if I multiply 256 by 2, I get 512. Those are powers of 2. So 2 to the first, so if I could do 2, 4, 8, 16, 32, 64. 64 times 2 is 128, and then 256. So 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be in between 2 to the 8th and 2 to the 9th. So I got a ballpark for x. That's pretty good. But I can solve it. I can solve this equation using the strategies in the last series of videos. I could solve it graphically. I can graph the left-hand side, graph the right-hand side, and I come up with an intersection point. And I get about 8.23, which is in the ballpark. X is going to be about 8.23, which is what I expect based on the values of 2 to the 8th and 2 to the 9th. Or I could solve it numerically and just kind of zoom with my table, and I could come up with a value there, 8.229 or so. So yeah, there are ways I can solve it, but this gets tedious. I need a quicker and faster way of undoing exponents and isolating variables that are exponents. So I could say, well, I need an inverse function. Remember, when we find an inverse, we swap the variables, x and y, switch and solve, and then we solve. But now I'm still in the same pickle. How do I solve for y? I need to get the exponent out. So I need to come up with, like, what's the inverse of this function y is equal to 2 to the x? So I'm going to try to figure it out, just pattern it graphically and numerically. You may have done this in Algebra 2. If you did, you get to see it again, you'll learn it better. So here, I'm going to graph y is equal to 2 to the x. So I'm going to have x and y, and I'm just going to come up with my little xy table. So I have, let's say 0, or let's do -1, 0, 1, and 2, and maybe 3. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 to the third power is 8. And I can graph these points. -1, I go up 1/2. 0, 1, over 1 up 2, over 2 up 4, over 3, and I go up 8, which I'm going to guess is here. And I end up with this exponential growth function that looks like this. Now, to get the inverse, remember the domain and range reverse. Inverse means reverse. So now I'm just going to do plot f inverse. I'm just going to come up with the points first. So I'm just going to flip-flop my x and y. 1/2, and the inverse goes to -1. 1 goes to 0. 2 goes to 1, 4 goes to 2, and then 8 goes to 3. And now I'm going to plot these points. So I go over 1/2, and then I go down to -1. I go over to 1, and I go up 0. I go over to 2, and I go up 1. I go over to 4, and I go up 2. I go over to 8, and I go up 3. And so here's what the function looks like here. And remember that this function, my exponential function, has a horizontal asymptote. Well, its inverse, if I remember graphically, if I reflect the blue, I get the red. The asymptote I'm going to reflect, and I'll get a vertical asymptote when I reflect it across the line y is equal to x. And so this part of the function ends up going like that. So there's f inverse, and here's f. So I can draw the inverse. I can come up with values for the inverse, but how mathematically am I going to define the inverse? And that's what we're going to define something called a logarithm. And let's just write some equations here. 2 to the -1 is equal to, let's see, let's just put some values here. I'll go back to blue. 2 to the -1 equals 1/2. 2 to the 0 equals 1. 2 to the first equals 2, and then 4, and then 8. I'm going to define something called a logarithm, which allows me to write equations that undo this exponentiation. So here I'm going to start with log base 2 of 1. So the base stays the same. So if I'm raising stuff to the power of 2, my log that undoes it is going to be base 2. So the base stays the same. Now the exponent is the input to the exponential function. So the exponent is going to be the output of the logarithmic function. And then the input, or the output of the exponential function, becomes the input to the logarithmic function. So now I'm going to rewrite each of these exponential equations. I'm going to write it as its matching, or its inverse logarithmic equation. I'm going to do that in red. So here I'm going to write log. It's log base 2 because the base is 2. And then the output becomes my input. And the input, -1, becomes my output. So log base 2 of 1/2 is -1. Same thing here. Log base 2 of 2 is equal to 1. Log base 2 of 4 is equal to 2. And then log base 2 of 8 is equal to 3. And this is how we define, we just define this mathematically because we need something to be able to undo exponential functions. We're just going to call them log functions or logarithmic functions. And this is how we write them, or this is how we write logarithmic expressions. The base stays the same. The base of our exponential function is going to be the base of our logarithmic function. It's 2 in all cases, just like it's always 2 over here. And then the inputs and the outputs flip-flop. The inputs here become our outputs here. And then our outputs to the exponential of the exponential function become our inputs for the logarithmic functions. And clearly I want you to notice here is logarithms, they end up being exponents. So logarithms are exponents. Write that down. Don't get a tattoo, but you can say logarithms are exponents. Logarithms are exponents. Chant that to yourself, write it in your notes, but these logarithms are exponents. Logs are exponents. They are what you raised, the base, the power, the exponent that you raised the base to get your output in the exponential thing. And that's where logarithms come from. So we can define a logarithmic function as simply the inverse of an exponential function. Here we have an exponential function, g of x is equal to 3 to the x. Its inverse function is the log base 3 of x functions. So the logarithms are the output values of the logarithmic functions. The logarithms are these output values. They're going to be the y values. So these y values, these are what we call, the y values for the log function are the exponents. So that's where log functions come from. In the next video, we'll be explicitly evaluating or rewriting equations and evaluating logarithms. At this point, annotate your notes. Bye.